for this next section, we're going to be solving logarithmic and exponential equations. They're just equations that involve logarithms or exponentials in the original representation of the equation, and then you got to solve them. Now, almost every one of these equations is going to require us at some point, going back to my 10 commandments of logarithms, to use this first commandment where you convert from a log to an exponential or exponential to a log. But in order to do that, especially with the logarithms, you've got to get it into one single log before you can convert. Here I have 2. So in this first example, some of them you'll have 1 to start with. But if you have more than 1, you've got to combine them together. And remember, combining logarithms together requires us to use properties 7, 8, and 9, where you take sums and turn them into products, differences to quotients, and constant multiples to powers. Alright, so on this one, I've got to get my logs on the same side of the equation and then combine them together. So I'm going to go ahead and subtract the log of x minus 2 from both sides of this equation. Now, logarithms, you can't just combine the arguments. You have to keep these as separate logarithms. There's a little bit of writing involved in this. The logs cancel out on the right side, and so I'm just left with the 1. Now here I have a subtraction, and the difference of 2 logs, according to property number 8, is the log of the quotient of the arguments. So I'm going to combine those using property number 8 and call it the log of 2x plus 1 over x minus 2. Okay, so that's property number 8. Allows me to combine the 2 or simplify the 2 logarithms. Then I'm going to go ahead and convert from the logarithmic form to the exponential form. And remember, you take the base, raise to the other side, equals the argument. Okay, so we're going to start now. Our base here, if you remember, on a common log is really 10. We just don't write it in. So we take our base, raised to the power on the other side, is equal to the argument, 2x plus 1 over x minus 2. Alright, now to solve this equation, I'm going to need to multiply both sides by the least common denominator. Remember, we do that for fractions. When there's fractions in an equation, I'm going to multiply by x minus 2. Those will cancel off on the right. 10 times x minus 2 is 10x minus 20, and that equals 2x plus 1. Of course, if I add the 20 to both sides and subtract the 2x from both sides, I'll get 8x equals 21, divide by 8, and x will equal 21/8. Now, what's interesting with logarithms is because there's property number 6, because of property number 6, we have to make sure that our logarithms are always defined, not undefined. And so this final answer needs to make the argument positive. If you ever plug in an answer and get a negative argument, you can't use that answer. Now here, 21/8 will make this positive, and it will make this positive. When you subtract the 2, it's going to be still positive. So this one's okay. But you always want to check, for negative arguments. Okay, always check that. This one works out, and so 21/8 is our answer. Now the next example I'm going to do is an exponential equation. And with this one, I'm going to start with a simple one, and then in the next video we'll do a more difficult. So 3 to the x equals 14. Now I could do this with a simple conversion from exponential form to logarithmic form. And if I did it that way, maybe I'll do that over to the side here. If I convert this, I would want my log with the same base of 3, but then I switch and use the 14 with the log, the x on the other side, and oh, there's my answer. It's log base 3 of 14. Very simple. Okay. However, there's another method that I think is going to be useful on more complicated problems, and that is to take the log of both sides. This can be done because logarithms are one-to-one functions, and if you use two equal expressions as the input for a one-to-one function, you get equal values. So you can use any logarithm you want, any base. Just for the sake of this problem, I'll use common log, and for some reason I prefer common log, but it doesn't really matter. You could use natural log if you wanted. And I'm going to take the log of both sides of this equation. Now there's a property, of course I want to solve for x. It doesn't look like I made this any easier, but there is a property of logs that says exponents can come out front as coefficients. And so I'm going to do that with this x. I'm going to pull it out. I get x times the log of 3 equals the common log of 14. If I were to solve for x here, I'd have to divide both sides by the log of 3. They cancel out on the left side, and x is equal to log of 14 over the log of 3. Now of course that doesn't seem to match up, but really it is the same answer we got before, because if I use my change of base formula and work it backwards, I will have the log, so the argument from the bottom becomes the base, and the argument from the top becomes the argument. So argument from the bottom becomes the base, argument from the top becomes the argument, and you'll notice I actually do have the exact same expression, log base 3 of 14. And just real quickly I can type that into my calculator. Log of 14 divide by log of 3, and I get approximately 2.402. Okay, I don't know which form of these three my math lab will want. You'll have to read the instructions. It may be different at different times. I'm going to take the simplified exact form without the rounding and call it log base 3 of 14.